All right, let's begin. So, last time we spoke about representing functions by power series, and we saw that we could get a lot of mileage out of the series for 1 over 1 minus x, which if your x is less than 1 in absolute value, you can kind of think of that as a geometric series where the r is x and the a is 1. And it turns out series are way more useful than you realize eventually. If you go far enough in math, you realize how important they are and how useful they are. But it begs the question, what if I want to find the series of a very weird function, a function that I can't really manipulate it to look like 1 over 1 minus x. Here enters the idea of a Taylor series. And Maclaurin Series. As a side note, which is a special kind of Taylor series. So this is going to be a way to express a function f of x as a power series. So I give you a random function. Maybe it's difficult for you to deal with in some sense, and you might have the idea, I want to write this as a series because integrating a power series, differentiating a power series, doing a lot of things with a power series is super easy because they just follow the same rules as a polynomial. And so you might want to think, how would I go about actually doing that, and when does it work? There are two main things that you need to get to this to actually work. F must be infinitely differentiable. You have to have a function that you can take its derivative, and then take it again, and then take it again, and then keep taking it forever. So the infinitely differentiable functions, that's the minimum requirement. Now once your function is infinitely differentiable, you can actually make a power series off that function. Now, sometimes, even though you can do it, doesn't mean it's going to be useful, because we know that series, they have 3 categories of behavior. They can converge everywhere on the real line. They can converge on some finite length interval, or maybe even an infinite interval, but maybe not the entire real line. Or they can, finite length interval, or they can converge at one point, which means the power series is only useful if you're at that particular point on the real line, which isn't very useful. So there are times when you can construct a power series and it's just not useful because the region in which it works isn't big enough for you. So in order to be useful, and this is something I'll make clear, f prime must not, or f to the n, the nth derivative, whatever derivative, no f to the n. No f to the n should change. I'm going to put in quotes here too rapidly. And I'll make that clear later on when I talk about something called Taylor's inequality. So, as long as you can find derivatives, you can do this infinitely many times, and all the derivatives behave there relatively nicely. They don't spike far up or spike far down very rapidly. And we'll define what it means to go too rapidly. As long as that doesn't happen, you can actually find a power series for a function that's going to be pretty useful. So how do we go about this? So we want f of x to equal a series, and goes from 0 to infinity of a n x minus x naught to the n. Now we defined this before. This is a power series centered at x naught, it's called. So So it's going to converge at x naught, or some finite window that you open where x naught is the center, or the entire real line. This is going to make sense in one of those situations. Okay? But how do you actually go about constructing it? Well, you would start by writing out a few terms. So if n equals 0, you'd have a0 plus n equals 1. You have a1 x minus x naught plus a2 x minus x naught squared plus a3 x minus x naught cubed. So write out one more. Plus a4 x minus x naught to the fourth plus, and this goes on forever, right? So we want to be able to take some random function that we're given, that we care about, and express it in this form. Centered, a power series centered at x naught. Now, a lot of people might think, it's obvious in hindsight when you kind of think about it, but there was no real way to actually, that was obvious to proceed here. But because we know this is a power function, it's just like x squares, x cubes, and we know something like differentiation actually breaks power functions down, the idea is just, well, if we could just keep differentiating, eventually we can break down all these x's and get something smaller, right? And maybe we can actually do something with that, and so that's what we actually do. So, now, so the idea is to keep differentiating. And then you kind of pull like a Donald Trump. We'll see what happens. Right? And you're going to notice that something really beautiful actually does happen. So let's actually start doing that. Let's find some derivatives and see if there's some kind of pattern that we can pick up on that we'll be able to construct this series. Now, the one thing that you would need for a power series, or to construct any series of any kind, you'll notice, is that we need a way to find the coefficients, right? So this part here is always going to be there. That's the part that I want. But I want to make sure that the coefficients are such that when I multiply these guys by certain numbers, they conform the polynomial to the function that I care about. So we actually need to figure this out. So how do I choose the coefficients so that this infinite polynomial will actually make sense with regards to this function? Well, so we know that the original function is a plus a1 x minus x naught plus a2 x minus x naught squared plus a3 x minus x naught cubed plus 4 x minus x naught fourth plus. Now here's something that you'll notice is pretty nice. If I were to actually want to break this down and find the first guy, a0, can you give me an idea of how I could figure out what a0 is if I wanted to solve for a0 and just get it, it's a number? Yeah? Well, f of 0 would f of x naught, right? Notice that if I actually if I plug in x naught into this, all of these guys would go to 0. And boom, that's how I find the first guy in this series. So I know exactly what that number is. That number is going to be the function I have evaluated at the point I care about. So now we're going to take a derivative. Now, the derivative constant goes to 0, so the guy I already found, he's now taken out of play. The derivative of this is going to be a1 plus 2a2 x minus x naught plus 3a3 x minus x naught squared plus 4a4 x minus x naught cubed plus da da da. And you play the same game. We'll take f prime evaluated at x naught. It'll kill all of these guys. And look at that. Now I figured out what the second number is. all I'm going to do is differentiate this function, which by assumption we can do. We can do it as many times as we like, and plug in the point I care about. That's actually going to give me the coefficient of the linear term. Keep playing this game. Differentiate again, that guy's going to go away. Differentiate again, here I'm going to have 2a2 and plus 6a3 x minus x naught plus 12a4 x minus x naught squared plus 1. Play the same game. If I take the triple derivative evaluated there, that gives me 2a2, which means f, this is second derivative, f double prime, if I could solve for the a2, this is just going to be f double prime evaluated at the point over 2. Keep going. Third derivative. It's going to be 6a3 plus 24a4 x minus x naught plus a bunch of other stuff. I can plug in the x naught and I would get 6a3, which means I can solve for the a3. That's going to be f triple prime evaluated at x naught over 6. Are you guys seeing a pattern? What is the pattern? So one thing, this is something that you're going to have to do every now and then, is to do a bunch of operations and try to find a pattern. This is kind of a tip that would help you in that regard. When you're trying to find a pattern, sometimes a lot of times, it's very useful not to simplify the intermediate steps because sometimes you might actually lose that pattern. So what do I mean by that? Here, I multiply the 3 by the 2 to get the 6. It's probably nicer to actually think of it as the 3 by the 2. Don't simplify anything. And so here, I can think of this as the 4 times the 3. And here, I would think of this as the 3 times 3 times the 2. This here is actually 4 times the 3 times the 2. So what you'll realize, this guy is going to be actually 3 times 2. You'd also notice that if you continue playing this game, the fourth derivative, that guy's going to die. This guy would just give you 4 times 3 times 2 times a4. You'll get the fourth derivative, evaluated at x naught, is going to be 4 times 3 times 2 a4, which means that my a4 is going to be f to the fourth derivative, evaluated at x naught, divided by 4 times 3 times 2. Now what's the pattern? Yeah.
And factorial.
It's a factorial in the denominator. What you can notice here, I can multiply this by 1 because it's the same thing. So this is f triple prime over 3 factorial. This guy here is f to the fourth prime over 4 factorial. This guy is f to the second prime over 2 factorial. You can notice that this is actually f to the first prime, right? When you write a power in parentheses, it means derivative, over, well, 1 factorial, because you can think of this as being divided by 1. This one you can think of as f to the 0th prime, no derivatives is the original function, over, well, 0 factorial, which is actually 1. And so, dot, 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 the pattern is the nth term, an, I can realize, I can figure out what that is by taking n derivatives, evaluating it at the point of interest where my power series is centered around, and then dividing that by n factorial. Now, at this point you can kind of see what I was talking about the derivatives not behaving too crazy. If this derivative actually grows faster than an n factorial would grow, basically if you throw this into the ratio test, that limit isn't going to converge, right? So you kind of want your derivatives to behave nicely with factorials, otherwise things can get a little bit too hairy. But I'll give you a more comprehensive definition of what it means to not grow too big. So that is how we find the coefficients. So this means I can take any function and I can write it as a series in this definite particular way. Take the nth derivative of the function, evaluate it at the point of interest over n factorial. That will be the coefficients of a bunch of polynomial terms. This here is called the Taylor series of f. Named after a mathematician, last name Taylor. At x naught, or you can think centered at x naught or about x naught. These are all phrases that you'd actually use. Let's actually do an example. I'll do an easy one. Maybe I'll also give you a definition here. I'll just tell you about the other one. Maclaurin series. If you center it at 0, where the origin is, we call that a Maclaurin series. So i.e. f of x, if you can express it as a series where you evaluate a bunch of derivatives at 0 specifically, times x to the n. This is called a Maclaurin series. And the center at x naught equals 0 is implied. Right? So whenever someone says Maclaurin series, they basically means a Taylor series centered at 0. So I believe in the bonus to the test, did I ask for Maclaurin series specifically? I don't remember if I asked for the Taylor series. Yeah, so in the bonus on the test, I asked you to find the Maclaurin series of a certain function. This is what I was talking about. You had to compute this series for the function cosine x cubed. Let's actually now do an example. This one's pretty easy. I'm going to just get through this one pretty quickly, just so you can kind of see how you would build up a Taylor series if you don't actually know one. So the Maclaurin series means you're centered at x naught equals 0. And basically what you want to do is you want to find a bunch of derivatives, try to find a pattern for the derivatives. So we know that f, the 0th derivative, is e to the x. So I'm going to evaluate that at 0, and that's just 1. And I can take the first derivative. Well, that's just e to the x. And so if I evaluate the first derivative at 0, I get 1 again. And I can find the second derivative, e to the x. Evaluate the second derivative at 0, and we get 1. I think you can see the pattern here. The pattern is pretty obvious, that f to the n of 0 is going to be equal to 1. So e to the x, I can actually write it as a Maclaurin series. This is n goes from 0 to infinity of f to the n evaluated at 0 over n factorial times x to the n, where my f to the 0 of n is 1. So I can really just plug that in. And ultimately, we tend to write it this way, x to the n over n factorial. And that is another way to think about e to the x. And you would also remember, that was a previous example. I don't remember, last lecture, 2 lectures ago maybe? I think 2 lectures ago. I think it was an example the last time we were in this room. We actually did that. Recall. This was absolutely convergent on the entire real line. So, e to the x, I can think of it as this power series. For pretty much all real x. There's no restriction. To the 1 over 1 minus x, we had a restriction. Our x had to be between minus 1 and 1. But the e to the x, I can think of it as this anywhere. Let's do a slightly more complicated example. That one was pretty easy. Let's actually find the Maclaurin series for let's say a sine function or a cosine function. Let's say sine of x. Did I ask you about the thing? That's about a cosine of x. Let's do cosine. Now, you didn't have to do this for the bonus, but I'm going to show you where the answer you would have used for the bonus came from. So, we're going to find the Maclaurin series, which means we're centered at 0. So, I care about the 0th function is cosine of x, which means if I evaluate this at 0, I would get 1. The first derivative is derivative of cosine? Negative sine of x, which means that if I take the first derivative evaluated at 0, I would get 0. The second derivative is minus cosine of x, which means if I take the second derivative evaluated at 0, that would give me minus 1. Third derivative is positive sine x, which means if I evaluate the third derivative at 0, I would get 0. The fourth derivative is cosine, which means if I took the fourth derivative evaluated at 0, I would get 1. And what's going to happen from here? Well, I'm back to where I started. So this pattern is just going to repeat. So basically what you'll notice for the cosine series is that at odd derivatives, the first derivative, the third derivative, the fifth derivative, the seventh derivative, it'll always give me 0. Now, otherwise, it will actually alternate. It will go with a +1, then a -1, then a +1, then a -1, then a +1, then a -1. So it actually alternates on the even terms. So here's how you'd actually construct that. So basically, f to the n, you'll notice, evaluated at 0, can describe it as a piecewise function. First of all, it's going to be 0 if n is odd. And it will give us, well, here's what we can do. We can do -1 to the n. Yes, -1 to the n if n is even. It's not how I want to write it, but it alternates is what I want to say. You can talk about specific even numbers on how it alternates, but I think you get the idea from that. So basically, here what we're going to do is to make sure we're only using even integers. How do you know that an integer is even? What's the definition? What makes an integer even? What's its form? 2n. We're only using even integers. Use 2n instead of n. So basically, every time you give me an integer, I'm going to double it so that it forces the integer to be even, right? Because I'm just going to ignore all the odd ones anyway, because they just give me 0. So my cosine is going to look like n goes from 0 to infinity of f to the n of 0 over n factorial times x to the n. Now, a couple things happen here. The derivative is going to alternate. Notice that at 0, I plug in 0 and I would get a +1, so that actually matches. If that didn't match, I would put like a +1 here to make sure that it starts out negative and then goes to positive. But actually just leaving it as -1 to the n, starting at n equals 0, will make the signs alternate how I want it. It'll start with a positive, then go negative, then go positive, then go negative, then go positive. And it's going to work for, well, instead of n, it works on 2 n's. So I'm going to put here 2n factorial. So all the factorials that it will work for is 0 factorial, then 2 factorial, then 4 factorial, right? This will make sure that that will behave that way. Plug in 0, I get 0. Plug in 1, I get 2. Plug in 2, I get 4, etc. And again, here I'm going to put x to the 2n instead of n. Again, to make sure that I'm only getting the even powers, x to the 0, x squared, x to the 4th, x to the 6th, so on. And so that is the definition. That is the Maclaurin series for cosine. Similarly, we can derive Maclaurin series for sine. You'll notice that the sine of x can be expressed as a series as a very similar pattern is going to ensue. The difference is the sine is going to work on the odd functions. So it's going to be x to the 2n plus 1, that's how you create an odd function, over 2n plus 1 factorial. Now, there's a reason why I'm putting these guys in boxes. You actually have to memorize these. So let me just write that down. So these are things where, unfortunately, you have to memorize them. So this is not something that I would give you on a test. These are things that you'll just be expected to know by heart. Almost in the same way that you know that the derivative of x squared is 2x without actually thinking about the power rule. It's just something that you know. The series for e to the x, cosine of x, sine x, and 1 over 1 minus x, you're expected to know these. You must memorize. So 1 over 1 minus x, you're expected to know that as a series. That looks like x to the n. You're also expected to know that only works when your x is strictly between plus and minus 1. You should also know that e to the x as a series, Maclaurin series specifically, but generally we think of it this way, is x to the n over n factorial. And this works for all x. Sine of x as a series is this guy, minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. This also works for all x. All you need to do is do the ratio test on this. It's 1 over factorial. The limit's going to go to 0, so which is always going to be smaller than 1, so that's going to converge absolutely everywhere. Similarly for this, it's 1 over a factorial. The limit's going to go to 0 when you plug it into the an plus 1 over an. It's going to always be less than 1, so that's always going to converge. Similarly, the cosine, should have started this up a little bit higher, is minus 1 to the n, x to the 2n over 2n factorial, where the 2n should be in parentheses. So these you have to know. So you'll be expected to know those by heart. And of course, once you know those, you should also be able to figure out anything that is some sort of variant on these, like a derivative or an integral of some amalgamations here. Maybe what I can do now is maybe do the bonus. Maybe I'll do the bonus as an example of how you'd actually use something like this. There are many ways. But for Calc 2, the principal thing that we would care about is integration and differentiation, because we're in Calc 2. So here's an example. Find the Maclaurin series of cosine of x cubed, and write out the first three terms. B. Approximate this integral 0 to 1 of cosine of x cubed dx using two terms of an appropriate series. Then I ask you to tell me how accurate your approximation is. So let's actually look at that. How you'd actually do something like this. If it showed up on a test or a final, it's definitely going to show up on the final. So, do you have to go through and do all these derivatives? No. You're expected to actually know what a cosine power series looks like. So, for part A here, you're expected to know that cosine of x, this is the series which means you're just going to plug in x cubed on that side. So that is going to give me that power series. So that's the power series. And this means the first three terms would look like, just going to start plugging numbers in. So if I plug in n equals 0, I would just get 1. If I plug in n equals 1, I would get minus x to the 6th over 2 factorial. If I plug in n equals 2, I would get plus x to the 12th over 4 factorial. And that's the first three terms. Approximate this integral. Now, we've been doing Calc 2, we've done a lot of integration, very complicated integrations, but you should be aware that your integration rules, none of the ones that we have is going to work on that guy. There's nothing, no technique that I've taught you could actually work that out. So, we are going to use a series. So I actually want to approximate this definite integral. One thing we can do is I can use the series that I just made. Now, it says I only need 2 terms, but I looked ahead and I know I want to know how good this is going to be. And I see that this is alternating, so I'm actually going to do it with 3 terms and just highlight the first 2 of them. So this is going to be approximately equal to the integral of now that's just integrating a polynomial. That's easy. That's x minus x to the 7th over 14, 2 times 7. And then 4 is 24, so this is going to be plus x to the 13 over 24 times 13. Between 0 and 1. Now, I was only told to do 2 terms, so I'm actually just going to focus on the first 2. So if I plug in 1, I get 1 minus 1 over 14. Plug in 0, 0, so that's actually the approximation. 1 minus 1 over 14, right? Or you can put 13 over 14 would be my guess as to what this integral will actually become. If we were in a universe that I could actually integrate it, doing this definite integral, that would be the answer. At least using 2 fractions. Let's see. I don't remember how I phrased it. How accurate is the approximation? Yeah?
Next term.
The next term.
That's over 13 24.
So notice here, if I had computed the third term, this would give me, I plug in 1 over 24 times 13 minus plug in 0. This would have been the third term. And so the answer would be the approximation above is within 1 over 24 times 13 of the actual answer. What is that exactly? That's like a decimal. So we can see it in percentage terms. Just an FYI. Like that's how you write the answer, but just as an FYI. 1 divided by 13 times 24. So, FYI, that's about the error. How far we are from the answer is about 0.0032. So we're good for sure up to 1 decimal place, but arguably 2 decimal places. Nothing's gonna round really. But the first 2 decimal places of this answer is actually going to be the first 2 decimal places of what the actual answer is. We're off by this, by 0.3%. Not actually bad. And that's because the cosine, it oscillates a lot for x cubed. But yeah, this is how you would actually approximate by the next term, which should tell you, how do you know? That was another part of the question. How do you know that that was what you were supposed to do? What would you say for that? What was the how do you know part?
The alternating series approximation.
The answer is an alternating series. There was a -1 to the end. So we just use one of our estimation techniques. The alternating series approximation theorem is what it is. That tells us that to approximate an alternating series, the first n terms will be the magnitude of the n plus first term away from the actual answer. So that's how you would know, because your answer was as an alternating series. Now there are 2 important questions here. So I know we did some trickery here with just rewriting this function that we couldn't deal with as a series because it was easier. But is this valid? Can we really think of cosine? Because that's essentially what I did in this problem. I literally thought of the cosine as being one and the same as this guy right here, right? Plugging something in here was the same as plugging something in there. And in fact, to even develop this power series, I had pretended that the original series for cosine was valid enough so that if I wanted to find cosine of x cubed, I can just plug in x cubed into that. But how do we even know that this actually does make sense to do that? Maybe this is giving us some other answer, not actually the answer of what this would have been if I could have integrated, right? You just did some hocus pocus and got a number. How do you know that that number actually makes sense? If I were to construct Riemann sums in like the old days, you know, back in Calc 1, like the old days, if I were to construct rectangles under that graph and actually add them up, right, and make a billion rectangles and add them up, would I actually get an answer close to this one? Because that looks way too easy. That's much easier than the Riemann sums way that we did in Calc 1. Is this actually a valid thing to do? I know we can do it, but that doesn't make it right. It doesn't mean it's useful. And that question we'll answer next time. The answer is yes. Just in case, it's like, no, none of it works. I guess let's get out of here. Calc 2 doesn't work. Yeah, planes would fall out of the sky if that wasn't true. It's not. Yeah. But we had to know it works before we actually started to build stuff with it. Do that next time.